We'll welcome our next speaker, Patricia Carvalho from SINTEF in Norway. She is also a professor in University of Lisbon, I think.
Not anymore.
Not anymore? Okay. But so we're moving from processing to characterization.
Exactly.
Yeah. So the floor is yours, Patricia.
Thank you. So I'll be presenting some work that has been developed during the project start. So I was given this task of talking about characterization, but I'm going again, as Alvici did, just change it a little. So I'm going to present some results of a meta-analysis that we have done with data from the literature. And of course, I will also use some of the results produced in START to illustrate some points. So just a few words about SINTEF. So I used to work here at University of Lisbon. Actually, I'm still affiliated with University of Lisbon because I never formally quit, and they cannot fire me. So we are sort of stuck with each other. So if you go to the University of Lisbon, my face is still there at the Department of Chemistry. But 14 years ago, I moved to Norway because they installed a very new center for electron microscopy, which is what was my expertise. So I moved there, and so SINTEF is a very big institution. It's a research institution, and it has two main poles, one in Oslo and another one in Trondheim. The one in Trondheim is connected to the Technical University of Trondheim, and the one in Oslo is connected to the University of Oslo, which is a classical university, so there's a chemistry and a physics department, and we work in close collaboration. I'm in Oslo. One thing about SINTEF is that we work with everything. There's always people working in all the subjects you can think of. Sometimes in European projects it's a little bit difficult to decide which are the tasks that we are not going to do at SINTEF, because of course we need to collaborate with partners. But so if you ever need anybody for anything that you can remember, I'm very easy to find, and I can direct you. Easy to find on the internet, and then I can direct you to my colleagues. So we are about 1,500 researchers divided between Oslo and Trondheim, 500 in Oslo and 1,000 in Trondheim. So Trondheim is bigger, and it's quite a lot of nationalities. One aspect which is important is that we are a foundational institute, meaning that we don't have very little money comes from the state budget. It means that all funds are competitive. So we don't get our salaries paid. We need to raise the money through funding. So what is the role of SINTEF in START? So we were asked to do, we have some minor other tasks in other work packages, but our most important role is in materials characterization, and that's why Philippe asked me if I could talk about materials characterization. So, moving to the talk itself, so just some words about thermoelectrics. So one aspect of thermoelectrics is that when we plot the transport properties as a function of carrier concentration, we see that there is very typical type of properties for each materials classes. And this means that most or the interesting thermoelectrics are semiconductor materials, so that's what we have to search base our search on. And there are several strategies, as Antonio referred, to improve the performance of thermoelectrics. Remember again that we are trying to increase the figure of merit, and that means that we want to decrease thermal conductivity and increase electrical conductivity. They are of course related, so it's not very easy, but there are some tricks. But I like particularly this picture that is in a paper by Snyder, quite early, 2008, where he explains that he and his group, that if you lower the thermal conductivity by, for example, scattering more phonons, you can lower from this is the lattice conductivity, thermal conductivity. You lower from one point to the other, and so you increase the ZT from 0.1 to 0.2 by scattering phonons, changing something in the structure so that you can have a lower thermal conductivity. But then, and this is very interesting, you need to optimize the seebeck. So if you lower the conductivity, if you lower the carrier concentration, you actually can increase the ZT to an optimal point. So sometimes we like to have a little bit less electrical conductivity than we might think. So tetrahedrite is quite a complex structure. It's a cubic structure. There are two very important sides, which are the copper sides, and they are represented here. So they're a bit difficult to see, but these ones have they are tetrahedrically coordinated, and these are trigonal coordinated. They're very different. So when we tend to replace, and this has been verified by neutron studies, when we substitute copper by 3D metals, which typically are 2+, they tend to substitute copper in these sites. And that means the positions 2D. This is very important because then we are letting the other coppers, which are the coppers that are rattling between two atoms of antimony, which have lone pairs, which repulse the copper, and copper vibrates in this plane. And by doing so, it's very efficient in scattering phonons. So we want to leave this sublattice alone, and we only want to mess with this one. This is very important because then we can decouple electronic and phonon transport, and then again we are in this cage situation, which is fortunate for tetrahedrite. So in the beginning of START, we went to the literature we knew that we had iron and we had zinc in the minerals, but we have many other things. And the idea was also, since we are doing mechanical alloying, was to maybe we need to add other things. What things should we add, and what are the concentrations that we need? So if you go to the literature, it's very confusing, because everybody does a study. They may even choose several compositions of the same elements, but then when they report it, they report the maximum ZT, which is never at the same temperature. So you don't really understand if this is the undoped case, which was measured 302. Maybe at 427, it's better than this one. So maybe you should not have doped. So it's very difficult to understand what should we do with the compositions. So first of all, which dopant should we choose? What's the concentration? Should we co-dope? We found out that it's a very good solution to co-dope, and especially because this is what happens in mineral tetrahedrites. And then, of course, we are mixing synthetic and mineral, and we need to come up in the end with compositions which are optimized or as close to optimal as possible. But it was very confusing. So this summer I had, last year I had a master student who came to stay with me from Portugal, and I asked her if she could perform a total literature review on tetrahedrites, and she did that. So she found 58 papers, 279 compositions, and approximately 8,000 points. Then I asked her, she was not very happy about it, but she had help from other people at SINTEF to extract the data. So what she did was she used AI tools to extract automatically when possible, and this was possible in more or less half of the papers. She could take out the individual points into a database. It's called plot extract. This is an automatic collection. Sometimes it didn't work. Half of the times it didn't work, especially when you have curves like this, like 2 axes often two axes, and then sometimes with arrows pointing or with a small inset in the graph, then it didn't work, and she had to do it by hand. But there's also a manual tool, which is quite nice to use, because you just need to, you define the axis, and then you point on the point, and then it automatically puts it in a table. You don't have to be, to just define the scale, and then you plot it. So this was also some help. But 8,000 points is a lot of points, so it was a lot of work. Oh, and another thing I didn't say. So there is a database which is very nice. It's a very nice initiative. It's in Japan. It's a Japanese group, and they are making a database, an online database with all the papers in the world about thermoelectrics. But there were only 20 papers on tetrahedrites, so it's not very complete for tetrahedrites. So maybe now we're going to publish these results, and maybe now we can ask them to incorporate our results there. Okay. So when we go to the literature and we get the points, this is what we get. It's a total mess. So you see there's a lot of zeros, and there's a lot of, look at this is very strange, these points here, but it ranges from, around this region, it ranges from 0 to almost 1. So it's very difficult to take any conclusions. But of course, this is not the correct way to plot it. I'll show another easier way, a better way in the next slide. But the conclusion we took from here is that there's a lot of weight from these points here that probably result from very poor processing, which are really putting the average down. So maybe instead of using the average these are percentiles, sorry, quantiles, that's the proper way to say it. These are quantiles. So maybe we shouldn't use the 50% to define the representative behavior of the tetrahedrites, but rather the 75%. So this is something we are trying to propose. If you want to have a benchmark, is our material better than the others? Should we compare it to the average? Should we compare it to the maximum? Because the problem of the maximum values that you see in the literature is that they also have a lot of propagated errors. And people don't discuss this, but most things are not reproduced. So you have 1.4 ZT, but does this correspond to anything? Or maybe it's not true. So we need statistics. We should have more points reproducing those values so that we can really rely on them. But then we found out that the best way to, the best way to represent this is using these hexabin plots, because then you can see because with this one, you don't understand where's the maximum of the dispersion for each temperature. It's just a cloud of points, but you don't really know if it's more to here or here, you don't know. But in this case, with the maps, with the colors, you can see where the center of the dispersion of the distribution is. And again, you see that there's a lot of weight here. So this is really pushing the 50% quantile, which is the median. It's pushing the median down. So maybe the 75% quantile is a better benchmark for us to compare with our lab results. But okay, here it's a bit messy because, of course, there's not so many points. So here we decided to investigate the temperature dependence when we have all the tetrahedrites. So all the compositions are there. If we try to separate, which is what we're doing here, we thought, okay, maybe this dispersion is because of the different chemical composition. So let's plot it for a single composition. The single composition with more points is the undoped one. And you look at it, and you see also here, it's also all over the place. So you see there's a lot of zeros here, then values which are much higher. So of course you have worse statistics because there's less points, but still it's very messy. So the conclusion was, well, there's not so much we can take from here, but now let's try to understand why is this. Why is there so much scattering in the data? So we try to plot the full data set again. So to make sure that we were normalizing in regards to the temperature dependence, we chose to plot everything at the ZTs at 350 degrees. This was also because at 350 degrees was the temperature that we have decided in start that it was the surface temperature for our devices. So, okay, let's plot at 350. So if we do that for all, the the data set, what we see is that if you prepare the samples by hot press or SPS or other techniques, which are very few, but still there are some, you get exactly the same. So the average is the same, and the standard deviation is more or less the same. So there's not so much we can take from the processing method, the sintering method. Then we started to think, okay, this was a problem we had a lot with the SPS person in START, which is not here today. At which temperature shall we produce the materials? We started with 500, but then we saw some things in the microstructure that we didn't like, and which I show you later. Then we started to decrease. We decreased until 340. But what you see when you plot, which is again very strange, is no matter what, the temperature on average, and these are the peak values, so these little stars are star data, so they're really good. They're the best for this class. You see that not only the average change, again a lot of dispersion, but also the best doesn't change. Different compositions, again, we are not normalizing, I mean the compositions are all mixed. But there doesn't seem to be a very important contribution from the sintering temperature, which is really, really strange. I mean, you go from 300 or 350 to 550, and you get the same type of properties. It's very strange. Then again, is it a problem of chemistry? Then we remove, we do it only for single compositions, and we did more than undoped. It's just that the undoped is the set with most data points. So we only have 52 data points at 350. And again, you don't see a very important contribution of the sintering temperature. Very strange. Then we thought, okay, let's look at density. The density is something that results from sintering. Do we see any influence of ZT, of the relative density on ZT? Again, relative density is complicated because some people, even for undoped material, single composition, the theoretical density used by the authors ranges quite a lot, which is very strange. Then some people put the relative density, but they don't give the theoretical density. Sometimes they give the density, and that's okay, but most of the papers don't give the density, they give the relative density. So it's a big mess again, but we try to plot, and we see a sort of a logarithmic kind of function, although we have here a linear. Of course, this is terrible because the scattering is huge, but what we can see again is that between 90 and 98, the ZT is more or less the same on average. Again, a huge scatter. Again, we did the same with undoped, a disaster. We can't take anything from there. So we thought, okay, what is going on here? Let's have a look at the microstructures. Another thing we did was to, okay, let's remove all the data which is below 95. Because you see here, this is very scattered and very bad. Remember also that the density enters explicitly in the calculation of the thermal conductivity. So if you use a very low density, you're going to have a very low thermal conductivity, and it might be wrong. And it can be artificial. And I think that's one of the reasons why we have this disaster here. But you see that here is very messy, but here it tends to be more uniform. So it's good that the samples that should be considered for any benchmarking or study should be with densities above 95. So what we have done, 77% of the reports in the literature have densities, relative densities above 95%. Then when we plot it, we don't see much difference. So we see very similar scattering, a little bit less, but it's not affecting. So when we look at the microstructure, what we saw was that in all cases, there was not one single sample that I've observed until now, and we produced hundreds of samples. There's always porosity. And when we look at low, when we do SPS, we only use SPS, so we don't have any hot press results. When we use low temperatures, what we see is that there seems to be some sort of a competition between densification and gas release, because we see a lot of pores and they are quite round. They're not typical of these pores. They are not typical of a consolidation, a sintering process that has not finished. They seem much more, especially at higher temperatures, that they are the result of a capillarity-driven pore equilibration. They're very small and they are round, very round. And round means always gas. So we are forming gas. It might be that it's just an SPS problem, but the thing is, since you see that all the methods resulted in the same type of ZTs, so it's probably a mixture. This is also possible to exist, but maybe it's higher in SPS, we don't know. One important aspect about tetrahedrite is that the mean phonon path is about the atomic distances, meaning that what is important is the rattling of the copper atoms. So if you put nanoprecipitates, if you put pores, they're never going to be efficient in dispersing heat transport phonons. So and this is documented in the literature. There are papers about this for tetrahedrite. So this in principle would be a bad thing. But these tetrahedrites have quite high values, so above 1. So we still don't know. We need to study. So these are just results just to show to you that we have essentially tetrahedrite. There's a little bit of fomentinite there, but they are essentially tetrahedrite. So when we do TEM on these samples, we see a lot of things, but just another thing here. So we have decided, so these are just 2 examples. They don't, with this study, we didn't want to make an exhaustive study of all the parameters because we wouldn't have the time. But this is just a composition that we have chosen in start because this is, we have zinc and iron which exist in the mineral material, so we need to have those elements, and this is just undoped. So if you look at these samples, the samples which are iron and zinc doped, this one was produced at 500. You see very big pores, in this case, larger than the ones before. I'll explain why in 1 minute. But what is important here, so in this case here, you have a magnification of this large pore, and there's something in there. So when you analyze this something, you see that you have iron, you have sulfur, and you have oxygen. So this is a sulfate. So this means that not only sulfur is sublimating because the pure sulfur has a sublimation point, as a boiling point, sorry, the word was not coming, a boiling point which is 400 and something. So it means that the vapor pressure is very high. Of course, we don't know for these compounds, but I believe that what we are seeing is sulfur sublimating. But in this case, what's happening is that if you have oxygen in your materials, which we always do because of ball milling, because at least from the powders, from the leaks, but also from the passivation layers in the stainless steel of the milling media. So this will all be incorporated in your material regardless of what you do. And so we'll always have oxygen. This might be actually a good thing because we are deoxidizing. Sulfur is deoxidizing the material. So oxygen is being removed out of the lattice, which might be a good thing or not. We don't know. So these very fine pores, they resulted from the, initially we started to make SPS consolidations with one, in the matrix, just one disk. And then in the industrial upscale, we started to make with more disks. When we made it with more disks, the porosity became much finer. We don't really know why, but this was a single disk, and this is this one here, which corresponds to the same type of material, was made with one disk. These two, they were made with 1 disk. So now if we try to zoom in, with TM. They were produced, in this case, we were studying the effect of nickel. What you see, I don't know if you can see it, but you have very, very small, these white dots you see here are pores. And if you increase the magnification, you see the pores. So this is a Haddaf image. I'm not going to explain what it is, but what you're seeing is the heavy metals, the heavy atoms are white. So when you see something dark, it's because you have less mass. So this is a pore, this is another pore, and you see that the sizes can go as low as 2 nanometers. But it's really, so all this, it's not noise. All these little things you see here, they are pores. The same here, this is for zinc. You see exactly the same thing, and you see more things. You see this contrast here, this is also strange. So there's probably a decomposition going on there, maybe a spinodal decomposition, because pure tetrahedrites has a decomposition. We see things there that are probably also indicating something like this. So, okay, so now when we try to, again, with the meta-analysis, with analysis of the many papers in the literature, we wanted to understand the doping. How much should we dope? Then when we plot, in this graph, you see here it's copper substitution, and here it's copper excess. So apparently from the literature, it's usually good. This is the undoped composition. The average is somewhere here. Again, look at the dispersion, enormous. But in this case here, there seems to be a trend that it's good to have excess copper. But of course, the data is a bit poor, but there seems to be indication that it's good. When these are again the quantiles, when you substitute copper, again here it's for all substitutions. We don't have enough data to study individually very well. You see that if you substitute very little, it's good. But then if you substitute too much, it's no longer good. So in terms of ZT. And this makes sense. Because what happens is that when you're, I have to go back just to show something that I forgot to mention. Because we are replacing, so copper is believed to be in a 1+ state, and when you're replacing with 3D metals, they are typically in a 2+ state. So you can never really replace all the coppers. The maximum you can replace is 2 coppers, because otherwise it becomes resistive, or it's not stable, which is what happens in some cases. I'll show you. So here is the doping conclusion in terms of the elements. So if you have all the elements here plotted, you see, if you consider, this is, I mean, cadmium, there's 2 papers on with cadmium. So this is not really, the statistics is very low. But in these cases, there are more papers, there are more studies, and there's something which is very striking, which is when you replace with 3D metals, so transition metals, what you see is that there's really, this is the undoped, and this is the best undoped, and this is the average, and this is the standard deviation. You come here and you see there's not so much of a difference. You see? There's one exception, which is iron, which is very unfortunate because iron exists in mineral materials. So you don't really understand with what should we dope. It's not clear, because what the conclusion is that the processing is so messy that unless we start to look at what the resulting microstructures are, we can't really infer much about the chemistry. So we need first to look at the processing, and then when things are really understood, then we can really optimize the elements. With doping, again, when you try to plot, here is the ZT at 350 with the composition. So here this is the undoped, and here we replace 2 copper atoms. You see that nickel seems to be quite okay. Zinc is quite okay until 1, and then it decreases, and iron is quite bad all the time. And when you try to see the electrical conductivity, thermal conductivity, and Seebeck, you see that iron is really the one that decreases mostly the electrical conductivity. The thermal conductivity decreases for all of them, again, more for these ones than for nickel. And here you see that nickel seems to always be increasing the Seebeck, and these ones might have a maximum. But again, it's very difficult to extract any any concrete ideas because it's very scattered. But this is some trends. These are some trends. The hole measurements are very difficult for these materials. We managed to do something, but it was very difficult because there's only 2 or 3 papers in the literature with hole measurements for tetrahedrites. We managed to measure. It makes sense, the results we had, but again, there's not so much data in the literature. Again, for nickel, we need to see, you see, it looks quite okay, right? Even if you replace 2. But if you look, when we replace 1, just one copper substituted, 1. When we go and look in the TM to see the microstructure, what do we see? Nickel is being segregated out. So nickel is not being incorporated. And then, of course, if nickel is not being incorporated, then, of course, the properties of the tetrahedrite are going to be more or less constant. So then we also did some DFT calculations to try to understand what was going on. There's many calculations in the literature, but they are all a bit different. They're made with different parameters, so it's difficult to take any conclusions out of that. And so we just made all the same, replacing 1 atom. And what you see is that when you replace zinc, copper with zinc, there's not so much difference in the band structure of tetrahedrite. The same with manganese. And then you start to see that you generate some defect states that go into the band gap. But all in all, they are quite okay because you still have the Fermi level within the valence band. So the materials are quite conductive, except for iron, because with iron, when you replace 1, what happens is that you have these very localized states that tend to decrease electrical conductivity because they work as carrier scattering. So the conductivity of iron is much less. But all of them tend to decrease because what happens is that the dopant electrons tend to fill in the holes in the valence band, and this means that the Fermi level goes into the band gap and the material starts to behave insulating. So I'm almost done. There's also much less work done on substituting antimony and substituting sulfur. And again, you see that the properties are not really the average and the peak. They're very, so it's difficult to choose one doping strategy. So this is my last slide. So so the main conclusions of this study is that it's very messy. We need to start to organize the thermoelectric properties a little bit better, and that's very interesting because that's one of the tasks of work group 1 in the cost action, which is to standardize the way properties are reported and to produce these materials. What we can conclude is that when doping. When you're talking about doping, we have to substitute copper, but in a moderate way. I didn't discuss the co-doping. In fact, if we use iron and we use another element, we get very interesting properties because they somehow hybridize. It's complicated what they do together, and this is something we need to study. But again, substituting not that much. But the main conclusion is that we need to start looking at microstructures because otherwise we'll never be able to reduce the scattering, and then we are just doping and doping and doping and taking conclusions, but nothing makes any sense unless we really understand the microstructure. That's the conclusion.
Thank you very much, Patricia.
Thank you.
Are there any questions?
Not totally. It is incorporated.
Oh, okay. Yeah, I was asking how why improve the electrical...
No, it is incorporated. But if you put if you substitute 1, which is about 3%, if you substitute 1 copper, you get a little bit of nickel segregating out. So you cannot fully substitute 1 copper in the structure. with nickel. But you do substitute, yes. It's very little nickel.
That probably depends on the process operation.
No, I don't think so. I think it's a thermodynamic.
It's really thermodynamic,
I think so. I think so. Because there's other papers where this has been reported. This is not only us seeing this. There's other papers where they. I don't think it's. I think it's if you anneal it, the nickel will be there, because nickel is fully. When you mechanically alloy, you don't see any segregation. So it's only during sintering that it. So if temperature is promoting it, it has to be thermodynamic. Yes, of course. I mean, we are, but it's 500. You can't go much higher than 500 because otherwise you melt.
Did you find any more dopants that have this problem of solubility? Or was it
Yeah, chromium, nothing goes in, or very little. Yeah. We tried many others because there was another study that we did, which was stability. We were trying to see, for example, tungsten, these big ones, whether we could make some kind of a passivation layer that would help us to prevent sulfur from going out. That was one of the ideas we explored. But these atoms, they are 3+, so they cannot replace copper 1+. It doesn't work. So I mean, maybe a little. But again, maybe these ppms of tungsten that we can put into the structure might be very good. Who knows? But we tried with one tungsten replacing one copper, and it was a disaster. Everything came out. It didn't even go in. Not in mechanical alloying, it wasn't possible. We always saw tungsten, niobium, titanium. We did all of that. Yeah, I can send, if you send me an email, I can send you the list.
Okay, there is one more question. We have time.
Thank you very. Okay. Thank you very much for the talk. I was a bit curious regarding your microstructural analysis on spark plasma sintered ceramics, because I saw that you mentioned variation of temperature parameter, I would say. Did you attempt variation of other parameters in spark plasma sintering to try to eliminate that porosity? So pressure, atmosphere, heating rates, etc.
We did a lot of in the beginning we did a lot of parameter change. The idea was more to try to get the samples without breaking them. So we changed pressure, and then we also anneal. So we keep the pressure until we cool down the sample, and there's an annealing step. We also, I mean, this was the conclusion that it was better for the mechanical integrity of the discs. We didn't change anything more, but there's one paper by Paz Vaqueiro on tetrahedrites. If you send me an email, I can send you the paper, where she says she uses an argon overpressure.
Right, because it creates pressure from the outside to inside, and
exactly.
then it helps close.
And then, but they don't, because nobody shows microstructures. So what people do is that they show, there's one or two microstructures. You show a nice microstructure, also with pores, but most people, sometimes they don't polish. They just have a fracture surface, and then you can't really see anything. So there's very little. So it's there's another thing you can do. It's pressure, overpressure, and something else. Now I can't remember, but
Nobody
I can.
Tried,
if you send me an email. No, vacuum is a disaster.
It's a disaster.
Vacuum is a disaster.
Because in some sintering techniques, you can use vacuum to remove the gas from the pores and help close porosity easier.
No, because you promote sublimation.
Right.
And this we know because we didn't present the results, but we studied the TG, the weight variation by annealing at 350 degrees in air and in vacuum. And in air, you oxidize, but you get, in some cases, you get to a stability point, and in vacuum, it's a disaster. Okay. It's really a disaster. You just, there's a lot of evaporation, and I'm guessing it's sulfur. We try to do mass spectrometry on the gas, but it's very little. We couldn't really pinpoint it very well, but I think it's SO2.
Okay, thank you.
Thank you very much. if there are not any more questions from the audience, we can go for a coffee.